I think I let my biases come through too much. Like trig integrals or trig substitutions. I love trig substitutions. That section was really messy and hard, but you know, I was just like, I love this. Let's go. And then partial fraction decomposition is really not that bad, but I personally don't like doing it. So I'm probably scaring y'all. It's fine. So if the degree of the top is at least the degree of the bottom, we just divide. But if the degree of our numerator is less than the degree of our denominator, that takes more steps. It's not more difficult, just takes more steps. So let's look at, we got all the rest of the videos are what to do in this case, basically. So here's a little fun fact for you. You can impress all your friends at parties, math parties, not parties. Anyway, so if each linear factor of Q, and let's call some linear factor of Q a sub I x plus b sub I. So it has a bunch of factors. They're all linear factors, so ax plus b. And let's just use a subscript because there's going to be a bunch of them. If every single linear factor of Q is distinct, so not the same, no perfect squares as the factors, then Q of x, sorry, P of x over Q of x, that's important, can be written as A1 divided by the linear factor. Some constant divided by that first linear factor plus some other constant divided by the second linear factor plus some nth constant divided by the nth linear factor. So if there's a bunch of linear factors, it's just we can decompose it into some constants divided by those lines. Now we secretly did this in this example 0, right? We factored, I said it was familiar. I never showed you that it really was familiar, right? I never foiled out the denominator. Our Q is x squared minus x minus 2. Yeah, I never showed you that that was the case. Yeah, if you factor it, okay, there's two linear factors here. They're distinct. It should be of the form some constant divided by the first linear factor plus some other constant divided by that other linear factor. Okay? That would have been a good thing to tell you. So let's see this in action. How do we find these constants? That's the fun part. Okay? So let's do an example. Example 2. Integrate 3x plus 2 over x cubed minus x squared minus 2x dx. Now I want to start this by reminding you and saying something I said and didn't always follow for trig substitutions. And that's, if you don't have to use partial fractions, don't use partial fractions. Can we do a u sub? Can we use arctangent? Can we use natural log? If so, let's do that. I don't want to do partial fractions if I don't have to. If we can divide, let's do that. We can only divide if the top were a third degree polynomial here. The top has to be at least the degree of the bottom for division to be useful. All right, we can't do any of that. Let's decompose. Kind of weird. I don't know. Let's just look. Okay, so what does the theorem say? The theorem says we can write this as basically some combination of its factors. We don't know its factors yet. Let's go off to the side. I sure as heck don't want to write this integral 50 times. So x cubed minus x squared minus 2x, how does this factor? Well, we can factor out an x. Anytime you can factor out a greatest common factor, that's always great. And then, oh, okay, we can factor this again. I think the same as we did before, x minus 2, x plus 1. Factoring is going to be important in this section. If you need factoring practice, that's fine. It's a couple classes ago. Don't beat yourself up. Just let me know. I can give you some resources. You can review it, and then you can be fine. If you don't review it and you don't know how to factor, then you'll have problems. So it's fine to have to go to review. Okay, so we have 3 linear factors. This one doesn't have a constant term, but it's still a linear factor. We have 3 linear factors. They are all distinct. So our property tells us that 3x plus 2 over x cubed divided by x squared minus 2x, that's a rational function. We know the factors at the bottom. Says it's going to be some constant plus the first factor plus some other constant plus the second factor. They're called A1 and A2 here. That's just so we can have a nice formula with n. But realistically, it's nicer to use A's and B's and C's. It's easier to distinguish them. So I'm going to write this not as A1, but just as A over the first factor plus B over the second factor plus C over the third factor. So it looks a little different, but that's exactly what that property said we can do. It's some constant divided by the first factor, some other constant divided by the second factor, and so on. Great. Oh, also the proof of this is pretty messy. We're not going to prove it. The book doesn't even prove it, okay? I find polynomials kind of boring to look at theoretically. I like using them, but the theory of polynomials and rationals is not super exciting to me, but if it is to you, let me know and we can go through it together. All right, so this is where I've been saying it for a long time, but this is really where the fun starts. How do we find A, B, and C? Well, we have a rational equation. How do we solve rational equations? Multiply by the LCD. Specifically, if we multiply both sides of the equation by this, all the fractions disappear. Why? Because this denominator is this, and of course, by construction, they all have that. Let's multiply both sides of this equation by x times x minus 2 times x plus 1, which again is the same thing as x cubed minus x squared minus 2x. These are the same thing. We're multiplying both sides of this equation by the same thing. That gives us 3x plus 2 equals a times x minus 2 times x plus 1 plus b times x plus 1 plus c times x minus 2. Why? Because we have to distribute this. And in the first guy, the x's cancel. We're only left with these two. In the second one, the x minus 2's cancel. We're only left with the other two. In the third one, you see it. So on and so forth. So now this is nicer. We still need A, B, and C. And there's 2 ways of doing this. A shortcut that'll sometimes work, and a long cut that will always work. We'll start with the long cut. This is like what we do in math, like with derivatives too, and integrals. We always start with the long method, and then you can really appreciate the short method. So this needs to be true for all x. This is what we want. We need this to be true for all x. So 2 functions are equal to each other, 2 polynomials are equal to each other if the coefficients of each of their terms are equal to each other. So the x squareds have to equal each other, the x's have to equal each other, and the constants have to equal each other. That's the only way. This is method 1. We call this equating coefficients. And this will always work, and it will only give you an answer if you're right. Whereas the other one, if you make a mistake, it'll still give you an answer anyway. So this is a great way of knowing whether you're right. And the method is exactly what it sounds like. Let's distribute. When we distribute or FOIL, we get x squared minus 2x plus 1x, so minus x plus 1. And then this one, distribute, is x squared plus x. And this last one, distribute, is x squared minus 2x. Now, all the coefficients have to equal each other. The coefficients of x squared have to equal each other. So what are the coefficients of x squared? Well, we can think of as 0x squared over here if we want. That's fine. So 0x squared is equal to, all right, this is going to be a times x squared. We're just looking at coefficients right now. Plus b times x squared. Plus c times x squared. Now, this might not seem very useful. We need three things, and this isn't going to help us find any of them. Have a little faith. Don't worry. Okay. And then we need the coefficients of x to equal each other, too. So we need 3 to equal minus a plus b minus 2c. And if you want, you can distribute out this in another step. So again, this is not looking good, Jason. But let's keep going. And the constant coefficients need to also line up. So 2 has to equal 1a. Oh, that's the only constant. Oh, thank goodness. We have a system of equations, 3 unknowns. Woo! That's going to be fun to solve. Well, luckily in this one, we already have one of them solved. A is 2. Oh, okay. So if a is 2, then what do these other two become? A equals 2. That gives us that 2 plus b plus c is equal to 0. And 3 equals negative 2. It's just, we have negative 2. Let's add 2 to both sides. So 5 is equal to b minus 2c. All right, so now we got these equations. Can we solve for a and b? All right, actually, let's not skip steps yet, Jason. This is 3 equals negative 2, right? Because it's negative a plus b minus 2c. And we can translate each one of these to something a little nicer. Let's move the constant over to the left. 2 is equal to b plus c, and then add 2 to both sides to get 5 is equal to b minus 2c. So now we have 2 equations with 2 unknowns. Remember your systems of equations. You can do the substitution method here, but the elimination method is actually, I think, nicer. If we multiply everything by a negative here, then we can just add our equations together and get a new equation without any b's. When we add these together, we get negative 7 equals 0b plus 3c. Oh, so c is negative 7/3. Great. We can use that with one of our other equations, any one of these 2 equations, and get an answer. So let's use one of these actually. Doesn't matter which one. Negative 2 is equal to b plus c. So b is going to be negative 6/3 plus 7/3. B is going to be 1/3. Great. We haven't done any calculus yet, but we're starting to get ready for calculus. So that's going to be our first method. And our first method is going to say, okay, how do we put everything together? 3x plus 2 divided by x cubed minus x squared minus 2x is equal to a, which we said was 2, right? Over the first factor, plus b, which we said was a third, divided by the second factor. What was our second factor? X minus 2. Plus c, which was negative 7/3, over the last factor, like so. Partial fraction decomposition gave us this. So now the question is, let's check our answer. Again, this is not a proof. The proof would be to combine like terms, combine the fractions. But it's a quick way to check your answer if you're on Desmos. 3x plus 2 divided by x cubed minus x squared minus 2x. And the question is that equal to 2 over x plus 1 over 3 times x minus 2 minus 7 over 3 times x plus 1. No, it's not. I'm glad I had the foresight to give you an example of how useful it is to check your answer. So negative 2 times negative 2 times positive 1 is negative 2, not whatever I wrote. A little fun fact for you, but all the calculations will update appropriately. The problem-solving method was the same. You can look at this if you want to fix the errors in your notes. I don't want to spend too much time on that because, again, it's just Algebra 1 systems of equations. And apparently I can't do it. And then you get this answer, and you can check your answer with Desmos, and you can see that, whoa, look, they're the same. Great. So that's the first method of partial fractions. I still haven't done any calculus yet, right? There's two ways of finding A, B, and C. This was the long method, equating coefficients. What about a different method? Let's look at the same guy. Okay. And let me come over here and look at the same guy. And notice that, remember what I said before. So this is our second method. We'll have it in blue. Strategic substitution. I like this name. This won't tell you if you make a mistake. Not in the same way the other one will. And I know it didn't tell me I made that other mistake. It tells you some other kind of mistake that you make if you do it. It tells us if your setup is wrong, not if your algebra is wrong. Anyway, this won't tell you if your setup is wrong, but this equation up top has to be true for all x. So specifically, if it has to be true for all x, so shouldn't it be true when x is equal to 0? Yeah, it must be. Well, what happens when x is equal to 0? Well, when x is equal to 0, the left-hand side is 0 plus 2. Let's do it. No, we can do it over here. And what does the right-hand side look like? A times negative 2 times positive 1 plus b times 0 plus c times 0. Hey, look at this. Do we get that 2? Is negative 2 times a. I don't even have the opportunity to screw up my foiling. A is negative 1. Neat. Well, all right, let's choose another number. Let's say, it's got to be true for x equals 0. Well, it's certainly got to be true for x equals 2 as well, right? When x is 2, the left-hand side becomes 6 plus 2, left-hand side becomes 8. The right-hand side, okay, that's 0. Plus b times 2 times 3, just plugging in x equals 2 into each of these. And when x is 2, oh, this last one's 0 too. It's a little cut off, but that's an x minus 2 factor. Oh, so we get that b, 8 is equal to 6b, and b is 8/6, which is 4/3, which is our same answer. Great. Not that I was worried. And I'm running out of room, so I'm going to cheat a little bit. And it certainly must be true when x is negative 1 as well. When x is negative 1, the left-hand side just becomes negative 1. We're just plugging in negative 1 into this equation. And then we get 0 plus 0. And then that last thing becomes c times negative 1 times negative 3. So we get 3c is negative 1. c is a negative third. And we can get A, B, and C this way. Also, those choices were not accidents. These choices were very intentional. You plug in x equals 3, you don't get anything really useful. These are the roots of that polynomial. X equals 0 was because there's a factor of 0. X equals 2 was because there's a factor of 2. X equals -1 was because there was a factor of -1. Now this won't work all the time, especially when we have repeated roots. We'll get into that in the next video, but a lot of times it'll work. Just make sure to check your answer, and this method's nice when you can use it, okay? But sometimes you will have to use the first method. We'll get into that in the next video. So let's finish this problem because we literally have not started the integral. What's example 2? Evaluate this integral. We've done no calculus. Nada. Let's get calculusing. The integral of, where am I? 3x plus 2 divided by x cubed minus x squared minus 2x dx. Okay. Well, we said that this integrand, we said that was, oh, I don't remember. -1 over x plus b, which was 4/3 times x minus 2 plus c, which was -1/3 times that last factor. Now we can do these integrals. Again, I've been skipping a lot of steps. I want to be very clear. This is -1 over x dx integral plus 4/3, the integral of 1 over x minus 2 dx, minus 1/3, integral of 1 over x plus 1 dx. And then again, we're really doing a u substitution on each of these, where u is x minus 2, du is equal to dx, and we get 1 over u. We have a second u that we call x plus 1, so its du will also be dx. If this is ever like a 2x plus 1, the u substitution becomes more complicated, and I might do that out. So be careful for that step that I'm not doing right now. We're going to get negative natural log of absolute x plus 4/3 natural log absolute x minus 2. We do need the natural log on all of these because we don't know whether x is positive or negative. Oh, plus c. All right. Fun little fact, by the way. This is sort of related to logarithmic differentiation. Pretty sure. I could be wrong about that, but I'm pretty sure it's related. Almost positive it's related, but this video is already long enough and I don't want to spend too much time on that. So those are the two methods, equating coefficients or strategic substitution. If you have non-repeated linear factors, we're going to do another one with non-repeated linear factors with a messier problem in the next video, and hopefully drive this concept home before we get into other forms of partial fractions. Because again, remember, this is only if the degree on the bottom is smaller, because if the degree on the bottom is bigger or the same, we use long division. And this is only if we have distinct linear factors. So there are other situations that we'll run into, but first I really want to spend some time on these two methods, equating coefficients and strategic substitution. All right. Let me know if you have any questions. Best of luck. Bye-bye.